Hi guys, let's quickly review what we have done in the last class. Okay, line by line, I'm going to review the code we made in the last class. Right, CLC, just clear command window. Okay, whatever there is, whatever there are. Okay, 1 1 1 1 2 2 2 2 whatever. Then CLC. Just you can clear the command window, right? And then here's RNG. RNG is just used to fix the samples randomly generated from the random number generators. Okay, so once you have the same the RNG number, then the same random samples will be generated from sort of for example here rand n or rand. Okay, here are the true values. Okay, so the first step is just DGP. Okay, so you are a sort of a god, and then you know all true values, and you generate the variables y. Okay, so this is what you believe. This is what you believe how the dependent variable y is generated from. Okay, so you believe that this y is generated from these linear equations, right? So then exciting variables times its impact on y, and plus something else which is not explained by the independent variables. Right? To do that, you will have to specify the true values, beta 1, beta 2, beta 3, and sigma square. Okay? You can choose any values, whatever is 1 or 0. Okay, in this case, suppose the second coefficient is 0. Okay, you pick any arbitrary true values. Okay, and sigma square is 0.5, whatever is 1.5, whatever. Okay, whatever. Okay, the intercept term is always fixed dependent variable, which is once. Okay, once, and then the second and third one are varying over individuals or time, right? So that's why we have this rand or rand n, whatever. So this it doesn't have to rand. It could be rand n, whatever. It doesn't matter. Okay, it doesn't matter. Okay, so rand is the random number generator from uniform distribution over the interval between 0 and 1, and between 0 and 1. Okay, okay, and so this is the matrix of covariates. So x1 is t by 1, x2 is also t by 1, x3 is t by 1. So that's why x is t by 3. Okay. So whenever you connect the matrices in a row, then we use this sort of the commands. Like here's brackets and comma. Okay. Let's practice here. Suppose a equals 3, 2. Okay, b equals I3, identity matrix, three-dimensional identity matrix. Then let me define C as A and B, and press enter. Right? Can you see that the first two columns are A, and the last three columns are B, and they are connected. Now it's 3 by 5 the matrix. And if you try to connect them in column, like let me define D equals A, now semicolon, and B. Let me press enter. Here's an error. Why? Because if you try to connect matrices in column, then the number of columns must be the same, right? Here, matrix A has the 2 columns, right? The number of columns is 2, but B has 3 columns. So that's why it's not possible to connect these two matrices in column, right? But if A equals once, say, 2, say 1,3, once 1,3, then now let me try again. D equals A semicolon B bracket, press enter. Now you see that the first row is what? The first row is matrix A. The last 3 rows are matrix B, right? So then now we have new matrix, and its dimension is now 4 by 3. So, right? Okay. This is how you connect the matrices in row or in column, whenever you want. Okay. Okay. Right. So then now we have true beta. Now we have true sigma square, and then here is error terms. Right? Error term has to have mean 0, right? So this is rand n means the standard normal distribution, and its dimension is now t by 1. So now we have cap t standard normal samples, okay, from this command, right? So y is cap t by 1 now. X is what? Cap t by 3. True beta is 3 by 1. This is t by 3, 3 by 1, right? That's why this multiplication is operable, right? And sigma square is 1.5. This is variance, but if you try to make the error terms variance equals 1.5, then the square root of sigma square should be multiplied, right? And then here is the random samples from the standard normal. So this is the how we generate the dependent variables, right? Of course, x is exogenous, so x is simply literally exogenous generated. So we have no idea how x1, x2, x3s are determined. They are just purely randomly given, right? But y is different. Y is different. Y is determined by x and coefficient and something else, right? So this is a model for y. This is DGP for y. So whenever we say data means actually y rather than x, because it's y generating process, right? Okay. So this is the area of God. Okay, this is the area of God, and then from this point on, now we are human beings, which means we don't know the true parameters, right? We have no idea what the true parameters for beta and sigma squares are, right? So that's why we estimate the parameters using econometric techniques. Here we are going to use ordinary least squares, and we know its formula, right? Its formula is what? X prime x times x prime y. Okay, x prime means transpose, right? So here is formula: beta hat equals x prime x inverse, here inverse of x prime x times x prime y, right? And now this, and then now we would like to see whether it's significantly statistically significant or not, right? To do that, we should be able to compute t values, right? To compute t values, here t values. Let me get the slide here. We want to compute t values. What do we need? We need what? Standard errors of the beta hat and beta hat. Do we have beta hat? Yes, we have beta hat here, right? We have beta hat here, right? And do we have standard errors of the beta hat? No, not yet. And to get the standard errors, what do we need? We need what? Variance of beta hat, right? Variance beta hat. Do we have variance beta hat? No. So then what's the formula? Formula is here. Variance of beta hat is sigma square times x prime x influence y. And do we have x? Yes, we have x because we have data. And do we have sigma square? No, we don't have sigma square because this sigma square is true values for sigma square, right? But we don't know true values. So that's why we use its estimate, sigma square hat. Do we have sigma square hat? No. We have to estimate sigma squares. And where's formula? Formula is here. E hat prime E hat divided by cap t minus 2. What's the E hat? E hat is what? Residuals. Do we have residuals? No, we don't have residuals yet. How to get the residuals? This is how we get the residuals. Residuals is equal to y minus x times beta hat. Do we have y? Yes, we have y because this is data. This is observable. Do we have s? Yes, we have x because this is observable as well. And do we have beta hat? Yes, we have computed beta hat using this formula. So using this beta hat, we can compute these residuals. And using these residuals, we can compute this sigma square hat. And using this sigma square hat, now we can get estimate for beta hat, variance of beta hat here. Sigma square hat sigma square hat times x prime x inverse, right? And using this variance of beta hat, we can compute the standard errors of the beta hat. Then using the beta hat and its standard errors, we can compute t values, right? So this is a sequence of the task. These tasks must be sequential. We should not change its order, right? For example, we cannot compute residuals without estimating beta hat first, right? It's not possible to compute t values without estimating sigma square hat first, right? So this sort of task must be sequential, and the sequence of the jobs is called algorithm. This is the algorithm, right? And given this algorithm, we work on the coding following the algorithm. Okay, so we estimate the beta hat using this formula. Given this beta hat, using this beta hat, we compute E hat. Using this E hat, and we can estimate sigma square hat. And where is cap t? How do you know cap t? Cap t is what? The number of what? Number of observations, right? Number of observations, right? Number of observations. And here, this is given here. Okay. And 3 is the number of independent variables. 3. How do you know the number of the independent variables? You can count the columns of what? The columns of what? Columns of x, right? We have 3 columns in x, right? So that's why this is 3. And using sigma 2 square, using this sigma 2 hat and the observations, then we can compute variance of beta hat. And then this is 2 by 2. Okay, this is 2 by 2. 2 by 2. And its diagonal elements of this 2 by 2 matrix is what? Variance of beta 1 hat and variance of beta 2 hat and variance of beta 3 hat, right? And we need its diagonal elements. So that's why we have diag. So diag of variance beta hat is now 3 by 1. 3 by 1, and we take square root. Okay, and this is defined as SE. Okay, and this is t values. Beta hat divided by standard errors. This is element by element operation. That's why we have dot here. And just for better looking, let me put space before and after this operation. Okay. Now we ask the MATLAB to display the output here. Okay. This is what we have done in the last class, and let me run it. Okay. Let me run again. Yes. Okay. Okay. This is not quite close to the true values. Let me try different one. Maybe we could we was just unlucky. 1 1 1 1. Yeah, closer. 2 2, whatever. Yeah, it's bigger. 1 6. Closer. Yeah, whatever. Okay. Right. So please try with different true values. Okay. Right.